Yes.
Okay, before starting, can you just like brief me out with your problem statement? What was your problem statement, and like how did you
A
just come up with?
problem statement was like um predict we have like motion data.
Okay,
Like a big problem was I'll show you the slide actually. A big problem was you could observe the motion of an object really easily. You can see how it's moving, what time it's moving, and all that kind of things. But it's hard to figure out the initial movement.
okay. So like, what real world problem are you solving with your project?
Like a real world problem include, let's see here, I put it. Um, Something with like planes have a big issue. You could see on how like the going up how to, the takeoff of the plane. Most crashes occur during the takeoff, and with our design, you're able to see what went wrong, like the angle that the plane went up at, and see if that was too much of an angle or too little, and also how fast did it go when it's going up. Like that's an example of plane.
Okay,
Basketball, if you're shooting a ball, right, and it's easy to track like specific points if you have a camera recording, but then you don't if you miss a shot, then you could see how you shot it and see if you could change the angle that you shoot it at.
okay, great problem statement. So like, just start your presentation from the scratch. Okay, you just have to introduce yourself. You have to
Yeah.
start the okay, great, works. Okay, okay, sure, you can start.
All right. The project on which slideshow. So the overview is our project is it's an AI powered thing, power engine that figures out how the projectile was launched, like the launch angle, the drag coefficient, and finally the launch velocity. And only using time versus position data, it makes an estimation and then makes a graph and then uses LLMs. It uses machine learning to estimate and LLMs to make the graph and also give it into human explanations.
Okay,
The problem I already explained to you. I could just skip this, right?
no, no, yeah, you can just see it again.
Read it again. We observe how and it's easy to observe how an object was launched. I mean, the data of the object, like the position on when you throw it, but it's hard to figure out the angle and velocity and other drag coefficients. And a thing would inference it by using like past data points. It uses the user uploads a trajectory data, and then it's processed, and then machine learning makes the initial estimate. Then it refines these estimates and then makes a graph, and then it uses the LLM to make an explanation. Real data was hard to get because we didn't have time to throw objects and figure out real data. So we trained it by using known physics equations, and then we just made up values from that equation and put it onto the training. So we came up with our own data. Then it uses noise to remove some errors and generalize the data into the real world. The machine learning part is how it inferences and makes a guess on how it looks. It doesn't uh it allows it for a the machine learning because it's trained on over like 10,000 um known like data equations. It's able to make a strong initial guess that noise helps remove error, and then we have a physics model engine to refine it.
Great.
Oh, whoops. Um, the physics-based optimization goes into the simulator that are um that help refine it by modeling gravity and air resistance. And this process, because air resistance, engines really can't figure it out, but some simulators can. We use it to make sure it sees the air resistance, a big part that's sometimes not accounted for. So this can count for air resistance and make sure that our solution is possible and is the most accurate to get. The LLM doesn't do any calculation optimization, but it receives. But instead of doing any more optimization, it helps interpret the data in a user-friendly way for people to read and what each parameters mean. Like if it was high angle thrown, it'd say how it's thrown up really high. Uh, it puts plots like data plots we're able to read and go through, and you could create tables of parameters, diagnostic errors, and it gives you summaries, and it just shows how physics how we could combine machine learning, LLMs, and physics to help solve hard problems, because figuring out launch angle and velocity with just time position data is normally not possible, but we're able to use machine learning to help get an accurate guess, more accurate than any human can. That's it. That's it.
Okay, so like, do you have the demonstration of your project?
I think I have to. Oh, I deleted Python. Let me see if I can get it up.
Overall, your presentation was good. You explained me each and every topic you had. So
Did
I just had one thing.
did Prever
Let's
show
say,
it to you? Because I think I deleted Python on my
oh,
computer.
okay,
Did he
so
show it
yeah,
to you?
okay, so yeah, like, are you able to like run the project or not?
I don't know which time. Did you just interview Prever before? There it is. I think I have it. So we're able to I put data in, and it makes a graph.
Okay,
So
so
and then this is the interpretation.
what does that graph represent?
These are the time position data I gave it. The line and inference is given here. So launch angle was 43, estimated to be 43.37. The drag coefficient was estimated to be 0.0246, which is really good. It's pretty accurate. The velocity was overestimated a bit by 13 meters. And yeah, they're like these estimates weren't far off at all from the actual.
Okay, like, can you just change the value?
What do you mean change the value of
Yeah, velocity and
increase the angle too?
okay,
So changes it again.
okay, great.
So new graph and drag coefficient was estimated 0.0209. Launch angle was really close, 58.1. And again, the velocity was shot up a bit by 8 meters. But again, it was able to figure out the drag coefficient, which is hard to get.
Okay,
And yeah,
great. Your project looks good. I was just bit confused. Like, What does both the line like? I have seen there are two
Oh,
lines. So,
this one, this is during testing. We're gonna remove it. The true line is this is what the actual model goes in. This is the regression for a real projectile. This is the AI's. This is the machine learning prediction. We have to
oh,
remove the true because when we give it out, but it
oh,
goes off the AI. It just shows how close it is with the graph. Like we're able to
oh,
see how it's
okay,
really close, especially up to here. It's almost identical. It's not far off at all.
okay. So, like, do you think your project is useful in like where do you see if this project goes to the real world? Who can use this project?
It sounds stupid, but I feel like me and him were talking about it. Um, if you want to figure out how, like, let's say basketball, gym trainers, they watch data and film to see what you have to improve on, right? And if you have a film camera of the ball getting shot, you're able to plot points of the position and time, right? It's hard to get an angle initial velocity though. So you're able to put it into here and then see if like and let's say he misses. You could see if he shot it there was not enough arc or if the velocity was too uh if he shot it too hard, so like the velocity or was too high or if he shot it too little, so the velocity was too low. That's the things.
Okay. Yes, you can turn off the presentation. Let's just have one-on-one interaction with you.
Turn off the presentation.
Yeah.
Yeah.